In this question, both training frequency, training duration, average training heart rate, and average training heart rate max were all the same. However, Dr. Gerd had a lower power output than us. Following training, Dr. Gerd had a greater increase in mitochondrial content. Why does this increase more while working at a lower power output? Our mass is going to be mitochondrial content. The inflow will be the synthesis of new protein, mitochondrial protein, through translation and transcription of DNA and mRNA respectively. PGC1-alpha is an activator of its own transcription, which further increases mitochondrial content through positive feedback. The increase in PGC1-alpha can be done through different pathways. The first pathway that activates PGC1-alpha begins with ATP utilization, which increases low-energy molecules such as ADP and AMP. AMP activates AMPK, which directly phosphorylates PGC1-alpha. We are able to suggest these increases based on the fact that the ACC is phosphorylated. Because AMPK phosphorylates ACC, we can assume that the same phosphorylation is happening to PGC1-alpha. AMPK can also be increased through intracellular calcium. Calcium activates CAMK, which activates LKB1, activating AMPK. CAMK also activates P38, which independently phosphorylates PGC1-alpha. We assume P38 is activating PGC1-alpha through the measuring of the phosphorylation of ATF2. A third pathway for increasing PGC1-alpha is through NAMPT, which is activated by AMPK. NAMPT is responsible for catalyzing the conversion of NADH to NAD+. This activates SIRT1. SIRT1 deacetylates PGC1-alpha, which activates PGC1-alpha. All these pathways lead to an increase in PGC1-alpha and therefore an increase in mitochondrial content. Our hypothesis is that the increase in low-energy molecules activates AMPK. The increase in AMPK activation increases PGC1-alpha and then mitochondrial content. Increases in mitochondrial content cannot be a result of Ca2+. This is because the student is working at a higher output, and that would lead to the opposite effect of the results. Dr. Gerd releases less calcium. Gerd is working at a lower absolute power output to achieve the same relative intensity, so he will produce more lower energy molecules. This would increase the phosphorylation of PGC1-alpha by increasing SIRT1 activity, further activating PGC1-alpha. In a study by McConnell and colleagues, 15 untrained healthy males cycled for 120 minutes at 65% VO2 peak. They trained for 10 days followed by post-training, in which they cycled for the same amount of time at the same absolute work rate as in pre-training. The results showed that ADP and AMP were lower post-training in all conditions. This supports our hypothesis. When comparing this study to our question, the students are more trained, and as a result, they would accumulate less lower energy molecules compared to Gerd. Gerd having more low energy molecules would lead to an increase in AMPK activation and more PGC1-alpha. We can conclude that the reason Gerd would have a greater increase in mitochondrial content compared to the students is as a result of lower energy molecules.